In Objective 2, we're going to start some of our shortcuts. The first one is the power rule. We're going to review the definition of the derivative first, which says the slope of the tangent line to a curve y equals f of x is the derivative of y equals f of x and is found by the limit as h approaches 0 of f of x plus h minus f of x all divided by 8. So this is called f prime of x. It may also be called dy dx. Our function is often called y equals, so we call it dy dx. This can also be called y prime, just like we write f prime. Okay. So one of the first shortcuts we have is the derivative of a constant. The derivative of a constant is always 0. That's a nice little shortcut. Here are some examples. We say y is equal to negative 3. Its derivative, y prime, is 0. Remember that this is because we're talking about slope of a tangent line. If we draw y equals negative 3, so we'll go down here, negative 3, y equals negative 3 is a horizontal line. What is its slope? This line has a slope of 0, and the slope of the line is the derivative. So the derivative of any constant will always be 0. So now we'll go ahead and jump into that power rule. It says if y equals a times x to the power n, where a is a coefficient and n, our exponent, is any real number except 0, okay, then the derivative of y, dy dx, or y prime, will become a times n, so that exponent comes down and multiplies with our constant. And what happens to x is our exponent, which was n, now drops by a power of 1, so this becomes n minus 1. And this just happens over and over for every expression that you have. So we're going to find the derivative of the following examples. Starting with the function x cubed minus 12x plus 5. So we get to use the power rule anytime we have all of our terms in one line, no variables in a denominator. Okay? And we're just going to apply the power rule here to each term, starting with f prime of x, to say this is the derivative of f. So bringing down the 3 out front multiplies with the current coefficient 1. We get 3x, and then we drop the power by 1 squared. Here, the power of x is 1. If we bring 1 down and multiply with negative 12, we still have negative 12. If we bring the power down by 1, we get a new power of 0, and x to the power 0 would be 1. And so we just end up with negative 12. And then last, we have a constant. And before we talked about the derivative of a constant is 0. So the derivative of 5 is 0. And we end up with 3x squared minus 12. Our second example, 6x cubed minus x squared plus x over 2. So again, all the terms are separate. We don't have any variables in the denominator. We can go ahead and apply our power rule. So to take the derivative of g, we're going to label g prime x is equal to 3 times 6, 18. X gets a new power, drop it by 1 squared. Here we bring down 2 and multiply with negative 1, negative 2. X gets a new power, down by 1 would be a power of 1. This is 1/2 x, and that x has a power of 1. So bringing down the 1 and multiplying it with the coefficient 1/2 will leave us with 1/2. And then x gets a new power. We bring the power of 1 down by 1, and we now have a power of 0. And again, x to the power 0 would be 1. You'll notice the two terms just had x to the first power. All we end up with here is the coefficient. Example 3, we have x squared minus 3 times the quantity x plus 2. Now we can't actually use the power rule yet here because we don't have all our terms multiplied out. So our first step is to actually multiply out the function. So this is still y. We have x cubed plus 2x squared minus 3x, then minus. And now that we have all of our terms laid out individually, we can take the derivative. So dy dx, or y prime, the derivative of y, we bring down 3 times the 1. X gets a new power, 2. Here, 2 times 2 gives us 4. X gets a new power of 1. Here, remember that anytime we had just an x term, the answer was just a coefficient. So that would be negative 3. And then anytime we have a constant, our derivative is 0. So this is all we end up with. Okay, and number 4. So here we had some multiplication we had to do first in this problem. Minus 5x squared plus 3 over x squared. We have some division to start with. So we actually want to do this division, and what we're going to do is just separate each of the terms and do our division individually. So we start with 7x cubed divided by x squared. So that's going to give us 7x. In our second term, negative 5x squared divided by x squared is negative 5. And our last term, 3 divided by x squared. So plus 3. And then in order to use our power rule, we need x to be next to the 3. And it can be any exponent except 0. So when I bring x squared up to the numerator, it does become x to the negative 2. Now I'm ready to take my derivative. The derivative of 7x. Again, anytime we take the derivative when there's just been an x, all we end up with is the coefficient, 7. The derivative of a constant is 0, so this term's gone. And then last, we multiply negative 2 with 3, we get negative 6. X gets a new power. Remember, we bring the power down by 1, so this becomes negative 3. And then to finish it off, we're going to go ahead and rewrite this so that our answer does not have a negative exponent. In this example, we are going to write the equation of the tangent line. To the function f of x cubed minus x squared plus 5x minus 2 at x equals 2. Something we were doing in objective 1. Now we get to use our shortcut. So because we want to write the equation of the tangent line, remember that in writing the equation of any line, there's only two things that we need: a point and a slope. Well, for our point, we know x has to be 2. To find the corresponding y value, we're just going to plug 2 back into our function. And we get 8 minus 4 plus 10 minus 2 is 12. So the point 2, 12. Now on to the slope. So the slope of the line, well, it's the slope of the tangent line, which is our derivative when x is 2. Now we need the derivative of f. Right here, we're going to write out the derivative. We're going to use our power rule. We bring down 3. The power drops by 1. We bring down 2. The power drops by 1. Okay, here, remember, the derivative of any x value is just going to give us the coefficient of 5. And the derivative of a constant is 0. So here's our derivative. Then we just want to plug 2 into the derivative. The derivative is the slope of the line. So f prime of 2 is going to give us 12 minus 4 plus 5, which is 13. We have a slope of 13. So all we need is the point and slope, and we can write our equation. So our tangent line here is y minus 12 is equal to 13 times x minus 2. The last few things we want to have here are the derivative of sine and cosine. We'd like to know what is the derivative of sine and what is the derivative of cosine. I could just tell you what these are, but instead we're going to derive their formulas, and to derive them, of course, we're going to use the definition of the derivative, which is the limit process. So we're going to do the derivative of sine first. So our limit process definition. We want to do sine of x plus h minus sine x all over h. So it's plugging everything in using our limit process. There's a few things we're going to need here in order to figure this out, and I'll come back and write them in as soon as we get to them. So first of all, in order to evaluate sine of x plus h, we're going to need to remember our angle addition rules. So from trig, we get sine x times cosine h, same sign, plus cosine x times sine h, and then we have minus sine x all over h. I have three terms on top now. not all three terms have something in common, but two of them do. Two of them both have a sine x. So I'm going to regroup these two terms here. Sine x cosine each, followed by minus sine x. And then we'll move this term here to the back. Plus cosine x times sine each, all divided by h. So I did this so that I could factor out that sine x. And to do that, I really don't need it attached to this term, so I'm going to actually separate my fractions. So I have sine x factored out of sine x cosine, leaving me with cosine, minus 1 over h. And then I have my last term, plus cosine x sine h all over h. So it's just the opposite of having a common denominator and adding the terms together. I just took it and split it apart. So the next thing we're going to need here are our special trig limits that we've covered. You'll remember that the limit as h approaches 0 of sine h over h, rather than x's, we'll have h's. This is a special trig limit. This value is 1. We had another one that used cosine. Cosine minus 1 over h, or it could be 1 minus cosine. Either way, this will give us 0. But this is the way it's written in our problem here. So this limit right here is going to give us 0. And you'll notice the sign x in there. Well, x is not the variable that the limit is using, so we don't really have to worry about it. It kind of acts as a constant. We can keep sign, and our limit here goes to 0. Over here, we're going to do the same thing. We have the sine h over h. That limit as h goes to 0 is 1. But the cosine x acts as a constant. We get to keep it. So cosine x times 1. And so this simplifies cosine. So that's basically like doing a little proof there of finding the derivative of sine x is cosine x. What does that mean? The derivative is the slope of the tangent line. So if I have a sine function and I draw a tangent line anywhere along my sine function, the slope is given by the cosine. Now the last one is derivative of cosine, which I'm going to leave you to do, figure out. I believe it is part of your homework. Okay. So we're going to derive it just how we did here. You'll end up using the same properties. Okay. If you're not sure if you got it right, go ahead and just look it up in your textbooks.